Good morning. Thank you for the kind introduction. Today we're celebrating 20 years with resonance frequency analysis, and I've been on the journey, so to say, for 20 years. So what I would like to do as a little introduction to Dr. van den Boogaard and Peter Moy is to discuss the history of the system and then to make some claims about the technique. Today, commercially, this is known as Osstell. Underlying technique is resonance frequency analysis. And I would like to do some statements before we start here. This is a non-invasive implant technique for implant stability measurements. And we know now from 20 years of use and research that it gives relevant information about the state of the implant bone interface at any time point during the treatment and follow-up of the patients. The question is, what should we have the technique to? Can we use it for something? Well, we can use it to monitor integration, as we will beautifully see in the coming presentations. We can use it to decide when to load our implants. We can use it to avoid failures. And finally, we can also use it to diagnose old cases that comes back to your office. The patient have a problem. It may be pain, swelling, whatsoever. With one measurement, you can actually tell if the implant is still integrated and have a good degree of stability or not. So you can actually exclude disintegration of the implant in your diagnosis. So it all started with this guy, a good friend of mine, Neil Meredith, who in 1992 got an idea. And at that time he was in Eastman Dental Institute in London. And the idea he got was from another part of industry. And historically, tapping has been used to analyze the integrity of glass and metals. And by tapping on the glass, you will have a ringing sound. And the different frequency of that ringing sound indicates different properties of the material due to cracks, impurities, and corrosion. So for instance, the integrity of train wheels are tested in this way. By tapping the wheel, and if there is a high tune, high resonance frequency, we know that there is no corrosion, no cracks. But if the resonance frequency is low, we know there is something wrong with the metal and the train wheel, which needs to be changed. So he thought that maybe we can use the same principle then to analyze the stability of dental implants in bone. So Neil is the inventor, but together with Professor Peter Cawley. And Peter is at the Imperial College in London, and his speciality is vibration engineering. So these two guys meet, and they start to think about how to do measurements using resonance frequency analysis on dental implants. So they do some prototyping of transducers. They have to do a setup, of course, of electronics to excite the transducers and to analyze their resonance frequencies. And this is before mobile phones was a great product. This was before electronics were very, very small and fast. So it means that at that time we were using quite big equipment, like an oscilloscope, a frequency response analyzer, and a huge PC. And this was a setup. And I met Neil in 1992, and we decided to work together. So we brought this machinery into the Bronnemar Clinic, where I was working at the time. And on your right-hand side, you see a prototype of a transducer which we used in patient. And one measurement could actually take 5 minutes in the patient. And in the first studies we published, we have quite a lot of patients with 5 to 6 implants. So we spent like a half an hour, 40 minutes, just to do the measurements in these patients. The principle at that time was to use an L-shaped transducer like this. And we have a cantilever beam on the transducer here. And on each side of the cantilever beam, there is a piezo element. And by introducing current into the piezo element, they will bend and stretch. And this way, the beam is excited and start to vibrate. And then we introduce a sinus wave of increasing frequencies. And at a certain point, the amplitude of the vibration will be at its maximum, and that is called the resonance frequency. And we see an example of such a curve, an amplitude frequency curve here. So that is the resonance frequency. And at this time, we were thus measuring implant stability in hertz or kilohertz. And as you know today, we're using another unit, the ISQ unit, so we're coming back to that. But this was the reality at this time. Neil moved actually to Sweden, and we worked together so much, so we decided to do this project as a PhD project. And he was actually my first PhD student. And in 1997, he defended this thesis, which included 7 papers. It was like a proof of the concept. We had in vitro studies, we had in vivo studies, and some clinical studies, just to prove that it was possible to use this technique to measure implant stability. And the findings from this work was that resonance frequency analysis is sensitive to interfacial stiffness. So if we're looking at an implant, we have different stiffnesses, so to speak. We have the stiffnesses of the components themselves, and then we have the stiffness of the surrounding bone, that is the biomechanical properties of the bone. But in these systems, the biomechanical properties of the components are constant. So it's actually changes and differences of the bone stiffness we are measuring with the technique. So this could explain why we could sometimes measure low resonance frequencies, and in other examples we could measure high resonance frequencies. What we also found out is that the resonance frequency analysis is sensitive to what we call effective length above the marginal bone crest. And this is an analogy with if you're using a tuning fork, and if you increase the length of the beams, the tune will become lower, the resonance frequency will decrease. So this means that if we have some kind of defect or marginal bone resorption around an implant, the resonance frequency will be lower as a physical effect, since the beam, vibrating beam, is becoming longer. So it means that the technique is also sensitive to identify marginal bone resorption. So the relation between stiffness and resonance frequency was first tested in vitro by placing an implant in light curing resin. And here we can see how the resonance frequency is increasing while the stiffness of the resin is increasing. And in this part, we have actually a linear relation between the time and increase of resonance frequency. And this is showing the relationship between exposed implant height and resonance frequency. And here we have implant placed in an aluminum block at different heights above the aluminum block. And we also have a linear relationship here. In 1996, we applied for a so-called demonstration project to the European Commission. And the name of this project was Improving the Success Rate of Dental and Craniofacial Implants Using Resonance Frequency Analysis. And we got the money, 2.2 million euros. And this money was used to induce a multi-center clinical study in Europe, where we wanted to test the RFA technique under clinically realistic conditions. But the aim was also to develop the technique into commercial available technique. So in 1999, the first company was founded, that was Integration Diagnostics. And the inventors were the owners together with other industrial partners. During this European grant project, the technique was developed, and now we could make use of developments within the mobile phone technology. So instead of using the oscilloscope and frequency response analyzer, we could now make this black box, which made things much easier. But still, we needed a computer then to read the measurements and make them into graphs. So this is the second generation of RFA measurement. And here we have the inventor doing a measurement on his former wife. This is, of course, a fake picture because she doesn't have any implants. Then we're entering the commercial era, and here we have the third hero who has been involved in the development of the technique, and that is Anders Petersson. Used to be the CEO of Integration Diagnostics, and now is the COO of Osstell AB. And Anders has been instrumental, I would say, for the further development of the technique. And what we realized during the first era, using the first and second generation, was the problem with the transducers. Each transducer had its own fundamental and unique resonance frequency. So this meant that we had to calibrate each transducer. And then after the measurements, we have to add or retract hertz in order to calibrate all the transducers. Another problem was that since we had to sterilize these transducers, they were very brittle and broke often, as well as the calibration blocks broke. So we had a problem of keeping all the measurements on track. So there was a need of improvements in this sense. The next generation, the Osstell machine, made use of calibrated transducers from the manufacturers. And we also introduced the ISQ unit. So instead of measuring in hertz, we are now measuring in ISQ units. So when you do a measurement, you get a reading from 1 to 100, based on the underlying hertz, but also based on the calibration on this kind of aluminum blocks. So it means that now measurements were directly comparable. With the wire technique, there were some drawbacks. For instance, we could, in a single-tooth situation, only place the transducer in buccolingual or buccopalatal direction. And we know from measurements we did in edentulous patients that if we are rotating the transducer, we can actually measure different stabilities in different directions. And usually the implant is more stable in mesial distal direction since we have more bone to support, and we have less stability in buccolingual direction since often the bone is thinner. And with this technique we actually missed the higher stability in mesial distal direction, and at that time recommendation was actually to place the transducer like that. So there was a need for, developing the technique. And I think this was a really nice thing when Anders came up with the first generation, which is called the Osstell Mentor, where we were using a smart peg. And this is a small peg which can be placed on any implant in any situation. And it's excited with electromagnetic pulses, and also the resonance frequency of the peg is measured with this transducer. And this transducer is actually vibrating in at least 2 different directions. So it means that it can measure the lowest and the highest ISQ in different directions. With the first instrument, we had to do 2 measurements in order to pick up the 2 different stabilities in different directions. So there was a need again then to develop this technique. And this is the instrument we're using today. That's the Osstell ISQ machine. And if there is a difference between the lowest and highest ISQ level, you will see that on the display as shown here. This is showing 57 and 68. So you have a low value and you have a high value. So it's easier than to pick up. This is my personal Osstell machine. It's in Ferrari red. Do you like it, Leonardo? Yeah, good. Yeah, thank you. Then, what have we learned during the 20 years? Well, it's a very short presentation this morning, but I can do some conclusions. And we have also been writing about this in this paper, which was published in 2008 in Periodontology 2000, which is a review paper on the technique. We know that implant stability can be measured then in different ways. It could be in rotational stability, it could be axial stability, and it could be lateral stability. And we are actually measuring lateral stability with the Osstell technique. So imagine that we are pushing an implant with a certain force in a lateral direction. This means that the implant will move in the bone. There will be some degree of displacement. And when this load is taken off the implant will go back to its original position. And this is different in different bone densities, for instance. So it means that a clinically stable implant actually exhibits mobility on the microscale when we do this kind of loading. So it means that a stable implant can actually display varying degrees of microstability depending on factors relating on the bone, surgical technique, and also the design of the implant. It is believed from the experiences with the implants, and we soon have 50 years of experience with osseointegrated implants, that historically we have seen more failures with implants placed in soft bone, short implants, grafted bone, in situations where the biomechanics are somewhat compromised. So we believe that implants with risks for extensive micromotions in the bone bed are more prone to failures than more stable implants, so to say. So if the RFA technique now is measuring displacement, the technique can of course be used then to identify these implants and also to monitor development of implant stability after implant placement. So we did a simple in vitro investigation where we placed implants into bovine bone specimens. With cone beam CT, we could measure Hounsfield units around the implants, and then we measured with the ISQ technique, and also we measured displacement. So we actually pushed the implant with 25 newtons for 2 seconds, and then we could measure how much the implant was displaced in the bone, and then we correlated this with the ISQ technique. And we see that it's a very nice correlation between displacement and measurement with ISQ. So we can say that the ISQ technique is actually reflecting the micromobility of the implant in the bone bed. And the factors deciding then how much the implant is displaced, or the ISQ value, is the degree of bone density and how well the implant is then engaged with that bone density. So it's again all about bone density, surgical technique, and the implant design. We can also conclude that high ISQ values reflect high stability and successful implants. We have seen that increasing ISQ values reflect a successful integration process, irrespective of which level we start. So the interesting part when using Osstell measurements is the low ISQ values, let's say below 60. And they may reflect low stability. They may reflect the presence of a marginal defect or marginal bone resorption. And falling ISQ values may reflect an ongoing failure. So let's say we start on 60, and then we see with time a slow decrease to 55 to 50. This is probably a sign of an ongoing failure. It could also be a sign of ongoing bone loss, since there is a geometrical relation between the distance from the top of the smart peg to the first bone contact. And in cases where we start with very high stability, let's say 80, 85 ISQ, we can see a decrease due to ongoing remodeling, but then there will be a flatten out effect around 70, 75. That is not an ongoing failure. So I think all these factors will be discussed by the coming presenters. And this is just a summary of the model, how we are thinking when using Osstell measurements. So this is day 0 when we place implants, and we will see different degrees of implant stability, maybe from 55 up to 85. That's quite normal depending on bone density and so on. With time, we will see changes of the ISQ value. For implants with low stability, usually we like to see an increase with time. If we have very high stability when we place the implant, it's not unusual that we see a decrease. And it seems like all implants are actually striving against an ISQ about 70, 75 after completed healing. And of course, inside this diagram, if we have implants going like that, that is a risk behavior, and then we have to cope with that, and I think Dr. van den Bogarden will discuss that. And finally, I would like to say a big thank you to the heroes of resonance frequency analysis. We have the inventors, Professor Meredith, Professor Cawley, and we also have Anders Pettersson. So thank you very much for listening to me.